Welcome to another episode of The Age of Science. In today's episode, we are going to talk about theoretical physics, how physicists go on modeling the universe, and how are they approaching unifying quantum mechanics and general theory of relativity to understand a small and large part of the universe. But what are the problems with it, and what are we facing today? Today's guest is Dr. Peter Woit, who is a theoretical particle physicist at Columbia University. Glad to have you here, Peter. How are you doing today?
Oh, very, very good. Thanks. Thank.
So let's start with, can you give us a general introduction, Peter? How did you get interested in theoretical physics?
Okay. Well, actually, since you're an astrophysicist, actually my original interest when I was a kid was actually in astronomy. So I was really fascinated by astronomy, and it was the time of the space program going to the moon and everything. And so I had a telescope, and I spent a lot of time outdoors with the telescope and trying to take pictures of stars and galaxies with the telescope and things like that. So that was my original interest. But then as I started learning more and more about astronomy and about astrophysics, what I really got fascinated with was by the fact that, that there was this, you could actually understand what was going on inside a star. For instance, there were these laws of physics which kind of explained, how stars worked and things. And that really kind of fascinated me. And then as I kind of learn more and more about kind of some more physics, I really got completely seduced, I think, by quantum mechanics. And by the quantum mechanics was just the most amazing thing in the world. And the relationship between quantum mechanics and mathematics really fascinated me and still fascinates me to this day. And so I ended up going to college and as a physics major. And but I spent a lot of time also taking mathematics classes. And I was at that point that I was really focused on studying theoretical physics and theoretical particle physics and quantum field theory. And then went to graduate school and then did a postdoc in physics. And then I ended up actually getting a job in the mathematics department. So for the last 30 years, I've been working in here at Columbia in the mathematics department. So I have kind of I had this PhD in physics, but I'm actually working among mathematicians. So it's kind of a multicultural kind of story, a little bit. So I have a very unusual background in that way.
So you've been bridging between mathematics and physics, and because usually mathematicians go on just sitting and proving things without, sometimes like the old French institutions that would try to completely go against Poincaré's point of view. Hey, we are going to go and start proving things. So you're the bridge now between the two, math and physics. That's awesome.
Yeah, well, I'm definitely kind of bilingual, and I understand both points of view fairly well, and I can speak both languages. And I understand very well the criticisms that physicists have of mathematicians, and to some extent they're valid, to some extent they're not. I mean, if you look at what mathematicians do in print and the way they kind of write books and papers and what they do in practice privately before they write things out of print are two different things. But I also stand, mathematicians similarly have a kind of a view of physicists that they often, do not know what they're talking about, and that they're just doing things in this very, very sloppy way, which often makes no sense. Many mathematicians I know actually started out as physicists, and most of them have the same story, that they were studying physics and they were studying classical physics, and everything made perfect sense to them. They thought this was great, and then they took a class on quantum mechanics, and the class just totally drove them crazy because they couldn't get a clear answer to what, why people were doing things this way or what they were doing. And so they decided that since this drove them nuts and they were enjoying their math classes, they should become a mathematician.
That's awesome. So for our listeners who are not physicists or mathematicians, I just want to ask these questions: how physicists or mathematical physicists or mathematicians go on modeling the universe? How the process starts, even, right?
Well, it's a big, so I think there's a great history of this, that really and if you go back to people like Newton, it really was unclear. The mathematicians think Newton is a mathematician, and physicists think Newton is a physicist. So they're really, the whole idea that you can actually use mathematics to model physics, was at first, I think, with Newton, in some sense, had the great success, and he was also then had to develop new mathematics in order to do physics. And so I think there's a long history of this kind of interaction between the two fields with with mathematicians getting inspiration for new mathematics from problems in physics, and physicists figuring out how to correctly formulate a theory in a useful way, and develop some techniques for really attacking problems based upon what they learned from mathematicians. So it's a long and kind of wonderful history, I think, and it keeps changing. The mix between how people work and what they're doing keeps changing, and to this day, I think it's a very complicated, unusual story about what's going on now. When you say mathematical physics now, it often means very, very different things to different people. They're very it's a long story.
So as far as since my background is physics as well, but the thing is, it started with classical mechanics, with Newtonian physics, and then suddenly the same world, the same nature was causing contradictions, and then general theory of relativity comes, and special theory of relativity to kind of cure these, contradictions that were thought. But then quantum mechanics jumps in, which is extremely radical, and it has a lot of differences with the classical physics, and it intrigued you when you were yourself a grad student. So what do you think about quantum mechanics? What did it change? Why it became very important?
Well, yeah, that's true. I mean, that's exactly why I've always been fascinated by the subject. I think you're right that special relativity and general relativity are, somewhat a natural evolution from Newtonian mechanics. They use the same kind of, in some sense, the same mathematical formalism. You're re-expressing the world as a partial differential equation and trying to solve it, and you're describing the world in terms of particles and fields in a very concrete, fairly what we think of a concrete way, using the mathematics which we always train students in our calculus classes. But the quantum mechanics is a very, very different theory. Yeah, it has a very, very different kind of point of view on what the world is, what a state of the world is, and what the right mathematics is for talking about it and for interpreting it. And so one of the things that's most fascinated me over the years is kind of this question of what's the, why is it like that, and what can you find a way of thinking about quantum mechanics in is there kind of a mathematical, what's the right mathematical point of view in which quantum mechanics becomes completely natural, and maybe even more natural than classical mechanics. And I think over the years I've kind of developed from what I've learned about what mathematicians do, what's interesting in mathematics, and what physicists do, and what they do in quantum mechanics, it's become fairly clear that that there is a certain mathematical point of view on mathematics where you think of certain ideas about symmetry and groups and representations as being a kind of a central unifying theme of the subject. And there is, quantum mechanics fits very, very naturally into that point of view. So there is a kind of way of thinking about mathematics, in terms of certain unifying principles which fit very naturally with quantum mechanics. And that's what I've kind of been most fascinated by in recent years. And I've been teaching this class, and I wrote a textbook about quantum mechanics from that point of view. And I still think there's a huge amount of anyway, there's a huge amount of inspiration you can get from that, and you can start to really understand why what a point of view on quantum mechanics in which it looks very natural, unlike kind of the way it's often taught, where it's just kind of this weird, crazy thing, which it's very unclear why anyone would have ever tried to do that.
So just for our listeners who are not technical, Peter, can you give an example of why one, like maybe physical experiment that can show them why quantum mechanics is so radical, like, in the sense of normal, behavior of the universe?
Well, I think maybe the thing which is, and one thing I start out when teaching this class, one thing that's the simplest thing to think about is actually the notion of spin of a particle. And so one thing that they discovered, when people were studying, starting to develop quantum mechanics and looking at atomic spectra, was that anyway, one whole aspect of quantum mechanics about why you understood why you needed to do this was this notion of atomic spectra, that if you go and look at you go look at the light coming in from the star, for instance, or something, and you see this pattern of absorption and emission lines of various things, and that actually tells you a lot about what kind of atoms this is coming from. And so a lot of the history of quantum mechanics was inspired by the development of that, and that's a complicated story. But one of the weirder aspects of it was the realization that all of these structures you were seeing, all of these spectra you're seeing, that they're that if you actually had a magnetic field, all of a sudden, in some, well, in oversimplifying, but in some sense, if you actually, things are right in a magnetic field, you start seeing a splitting, that these all these energies that you're seeing in these spectral lines all of a sudden split in two, right, by a slight amount, proportional to the magnetic field. And so, in what this ends up being about, one way of thinking about it, is that our fundamental particles that we know have this notion of spin, and in some sense, the simplest particle to think about might be an electron, and it's a fundamental particle, and it does a lot of very complicated things when it's moving, or whatever. But if it's just fixed and sitting there, you don't worry about its motion in space and time. It has this extra degree of freedom, which it has this kind of twofold degree of freedom, which you can see very nicely if you apply a magnetic field to it. It'll split it. What looked like something with a certain energy will split into something with two energy levels. And so I think, thinking of, and if you want a very precise way of stating the problem, the question is to think about, assume that you have an electron and that it's essentially very, very massive, but that it's very massive compared to all the energies that are around. So it can't really move. It's just sitting there. And you can imagine, how am I going to describe this electron and what it's doing as it sits there? And so you need this you need this notion of spin to describe that. And the mathematics to describe it is, it's something which it is not that elementary. But it's basically just linear algebra. When we teach linear algebra classes, we teach about matrices and vectors, and the description of a spin one half particle, a spin 1/2 degree of freedom, really can be done very simply just in terms of 2 by 2 matrices, but using complex numbers. So it's different mathematics. That's mathematics that you don't ever really see in classical physics. That complex matrices just don't really. They may be useful for calculational purposes, but they're not kind of fundamental objects. But if you want to understand what this kind of very fundamental spin 1/2 degree of freedom of a particle, which it's very quantum mechanical, it's not a classical thing, it can be understood, and it can be understood just in terms of that if you want to describe the state of the particle, you have to take a vector with 2 components that are complex, and if you want to understand what it's going to do and what's going to happen if you start observing it, or how it's going to evolve in time, you have to think about 2 by 2 complex matrices. So it's it's from a classical point of view, it's very unusual mathematics, but it's not that difficult. It's not that difficult mathematics. It's something we teach in our linear algebra classes. So that's, I think, from the point of view of what's the fundamental mathematics going on, that's I think the simplest example to think about. Then once you actually get into the question of what happens when you start interacting with this electron and trying to describe it using that way, and what the physical implications are, that starts to get a much more complicated subject.
Yeah, exactly. So the thing is, from the time quantum mechanics was introduced, physicists are trying to kind of unify that with general theory of relativity. So kind of they can have one theory for small scale to the large scale. Right now we have them separated. So why quantum mechanics and general relativity don't add up together, or they have conflicts?
Okay, yeah. Well, anyways, that's a big and very open question. Yeah. So the so we anyway, so yeah, we know that we want to describe things like well, we actually have a very, if you start maybe with a simple problem of how do I describe an electron, you know, I was telling you that, you know, you can use simple linear algebra to describe what its spin degree of freedom is. If you want to describe how it's going to move and how it's going to move, you need something called the Dirac equation, and that's a fun. And then if you want to describe how it's going to interact with forces, with electromagnetism and electromagnetic fields, you need to couple it to electromagnetism, and it becomes a somewhat complicated story, but there is a kind of fairly beautiful theory we have which describes it. It's called quantum electrodynamics, and that theory, you know, to describe it and work with it is fairly tricky, but it's kind of well known. It was people first started looking at it in the late 1920s, and by the 50s people had figured out how to do calculations in it, and it's now quite well understood. So that's all well and good, but the problem really comes about more if you decide, okay, now what about the gravitational force on this electron? Okay, so if you have a fixed kind of background, which general relativity tells you that you've got some nice curved space-time or something, we know how to describe how an electron is going to move in that fixed curved background. But the problem, what we don't understand is we know that in the case of electrodynamics, you know, when you move electromagnetic fields get quantized. There are these things called they're photons. It's not, so you don't just have to worry about how electron is going to move in a background fixed electromagnetic field. You have to actually worry, what's the electromagnetic field going to do? What's its dynamics going to be? And it's going to get quantized, and you're going to have photon excitations of the electromagnetic field are going to be there. So what we don't really have is a completely consistent theory of what will happen for the gravitational field. So we know there's a gravitational field classically. We know how we know that it's interacting with these quantum matter particles. By analogy with electromagnetism, it also should be a quantized field, and so there should be gravitons, but we don't have a completely consistent theory of gravitons, of the quantized gravitational field. That's really what's lacking. And if we try and do it in the ways in which we have handled other quantum fields, you get technical problems which which people have not found a completely consistent and convincing kind of way around at this point.
So right now, yeah, we are kind of having problems to explain these phenomenons or kind of make the gravity come to the picture. Yeah. But so usually when I see the unified theories, the theoretical physicists fall to a major category of saying we need to change general relativity to make that match quantum mechanics, right? So to kind of, the quantum mechanics is more fundamental. But yeah. Roger Penrose, on the other hand, like thinks, no, they are not kind enough to general theory relativity. It has been proven right for decades, and lots of experiments are showing it's correct. So why don't we go the other way around and meet in the middle? So maybe quantum mechanics needs to be changed as well, right? So what do you think, Peter?
Well, I think I'm on the side of that quantum mechanics is, I don't know, I have really kind of become convinced that quantum mechanics, well, first of all, it depends kind of what do you mean by quantum mechanics? So I guess the way I would say it is you quite possibly need to generalize the way you think about quantum mechanics in order to capture what's going on in general relativity. But the some of the underlying fundamental structures of what we normally think of as that are fundamental to quantum theory, those are actually mathematically very rigid and I think very beautiful. And they work, since everything we found, they work so well. The evidence that I see is more that, those are working so well that, you know, there's you can't change those in a completely fundamental way. Maybe you can extend them and get a deeper insight in them, do something, but that's just works too well and is too rigid. You can't. I mean, the problem with saying, oh, I'm just going to, yeah, I'm going to kind of give up on quantum mechanics and reformulate it more in terms of kind of classical general relativity. There's no kind of obvious way to do that in any. You're throwing out so much that it's hard to know what you've got left to start with that can go anywhere. And most attempts of people who want to pursue that, I think they end up with kind of too little to build on to work with. Yeah, I mean, Penrose, I think, is a fascinating character. Like, he's one of the great people of the subject of mathematics and physics, and one of the great thinkers about general relativity. And he, so you know, some of I think his prejudice, I think he's, yeah, some of his belief that general relativity is going to fundamentally change the measurement problem in quantum mechanics, and that's going to solve the problem. I'm not convinced by. I don't think he has much of a solid argument. I mean, some of the other things that he's done, he's arguing that, which I would say are actually a fundamental change in general relativity, where his notion of a twistor theory, that you really should base general relativity on a very different ideas about geometry than people are used to. These ideas of twistor theory, those I think are completely fascinating. I'm become a complete convert, especially the last year or two. I've been doing. I see some amazing things going on there, so I've become a complete convert to his to those parts of his ideas about twistor theory. And I think, yeah, they're to my mind, one of the great questions is kind of how to bring together twistor theory and quantum theory. And it's true, you really need to extend your ideas about how quantization works in order for it to fit well with this twistor theory. So I'm partly on board with Penrose in some ways, partly not.
So can you just maybe give a brief explanation for our listeners what twistor theory is talking about? Maybe like listeners will be like, oh, what is the twistor theory now? Okay.
Yeah, well, the problem is it's very different. It's a very different way of thinking about geometry. So, and so the way we're used to thinking about geometry, you have this space, and you've got kind of point. You're interested in describing. You have points in space, and then these things move around. So you extend this to time, and if you study general relativity, you get into the complexities of now your space and your space can be curved, and your space and time can be curved, and so but you fundamentally have kind of this four-dimensional array of points, a three space-time and one time-dimensional array of points, and things are moving around in them, and so you think of that as you're looking at this chunk of space in front of you, and things are moving around in it. Now, I think the thing there are a couple things to say. It requires a bit too much math to really to really tell you the story of exactly what twistors are. But there are a couple things that I find completely convincing about it, which are which you can understand. So maybe the first one is that from Penrose's twistor, in twistor theory, the fundamental object are not actually points, but they're actually physically light cones. So so what Penrose says is you shouldn't really be thinking about points moving around in four dimensions. You should be thinking about the fundamental object is a light cone, which is kind of the sphere that when you actually look, when your eyes look, you're not actually looking at this chunk of space-time. You're actually looking as if there's a sphere around you. There's the screen of light with patterns on it. That's what you're seeing. And what you're actually seeing is the light cone at some point in space-time. You're seeing the light cone. You're seeing all possible rays of light that can come to you. And so what Penrose says is that thing that you see when you're opening your eyes, the light cone, that is the fundamental object. You should be, those are the basic things, which structures that make up space-time, and that a point is a derived concept. You shouldn't really think about points in space and time. You should think about light cones, and what you want to, the fundamental mathematical object in your theory should be a light cone, and a point in space is a light cone. And anyway, so that's the beginning of a, you then have to kind of develop some mathematics to kind of make sense of that way of thinking. But that's one thing that I find quite nice about this. The other thing is the within the standard theory of general relativity, or way of thinking about general relativity, this spin 1/2 thing, the fact that particles have spin 1/2, is actually very alien and very difficult to describe. You really can't. If you go look at a general relativity textbook, you'll find and see how they describe fields and particles. You'll very, very rarely see them talk about how you describe a spin 1/2 particle interacting with a gravitational field, because it really just doesn't. The most common kind of mathematical framework used to explain general relativity, it actually doesn't fit. You really actually can't do it at all. So you have to kind of develop a mathematically more sophisticated way of thinking about general relativity and do it in a certain way, and then you can include spin 1/2. But it looks like a very artificial construction. But on the other hand, from Penrose's twistor point of view, one way of saying that, the actual points in space-time are these light cones. Another way of thinking about it is that he said, from a twistor point of view, a point in space-time is described by a complex two-dimensional space. It's a complex two-dimensional space, and it lies inside a complex four-dimensional space. And so twistor space is the complex four-dimensional space, and a point in space-time is a complex two-dimensional space. It's kind of a plane, if you like. It's a complex generalization of a plane lying in four-dimensional space. And the spin 1/2 degree of freedom is described by a complex two plane. It is that plane. So it's a completely tautological explanation for where spin comes from. From the point of view of this theory, a point is a complex two-dimensional plane. And you want to know, why is spin appearing? Well, it's that complex two-dimensional plane. We're done. And so it's a completely tautological explanation of why spin is fundamental and where it comes from. And it just kind of, it just kind of completely blows my mind and convinced me that just that argument means that twistors have to be the right way of thinking. And
that's a very interesting. I've never heard of it this way. So it makes a lot more sense to me. But just asking, what is that four-dimensional, twistor space? That it's just a mathematical construct that.
Yeah, it's just a mathematics. And so there's a long then story about trying to turn this into a really useful theory. And I think and I mean, there's a long story about it. I think one way to say about what happened with that theory is that it's really a beautiful idea. Penrose came up with it in the 1960s. There was a lot of work on it in the 70s into the 80s, and then that kind of slowed down. And one problem is that people never managed. People were hoping that they could use it to resolve this problem of how to quantize gravity. And what happens, actually, I think the subject hit somewhat of a technical roadblock, which is that, actually, when I say, it's a bit more complicated. When I say that a spin 1/2 is a complex two-dimensional plane, non-relativistically, that's actually true what the spin 1/2 looks like. When you actually think in terms relativistically about massless particles, or particles whose masses are small compared to the energies you're dealing with, then the story of the Dirac equation is more complicated. You have spin 1/2 particles they can come in kind of so-called left-handed and right-handed versions. They have chirality, that fundamental massless particles they're described by a two complex dimensions, but there's two different kinds. There's the right-handed ones and the left-handed ones, and it's a long story. But in some sense, the defect of the problem with general relativity, as we normally understand it, is that it's it's parity symmetric. It doesn't see any difference between the left-handed degrees of freedom and the right-handed degrees of freedom. They're supposed to be treated the same way. Whereas the story I just told you, actually from string theory, it treats one chirality is fundamental and is very different than the other chirality. So twistor theory is it's very parity asymmetric between right and left-handedness in a very fundamental way, and general relativity, as we understand it classically, is not. So that creates a fundamental problem, which Penrose calls it the Googly Problem, because evidently people who know about what is it? Yeah. Anyway, this very British sport of I'm losing the word, but anyway, yeah. So there's a British word which he thinks captures this from cricket. Yes, cricket. In cricket, there's a question of I guess how a ball spins at cricket is divided as there's a googly comes in, and so he called that the Googly Problem, and that was never resolved. So that's anyway. So that's somewhat a roadblock, and I actually anyway. So one thing that's fascinated me is I kind of start to see some ideas about how you may get around that roadblock and using integrate twistor theory and resolve these problems about quantum mechanics. But this is kind of what's fascinated me and most recently, especially the last year or two.
That is interesting. So you mentioned the string theory. I actually wanted to talk to us about string theory for sure, because that's another route that has been taken to combine general theory of relativity and quantum mechanics, kind of. So I just maybe briefly, like for our listeners, again, maybe they're not technical, to understand what string theory is actually talking about, like.
Okay, yeah. So again, so to back up, so string theory has an interesting history. It during the 1960s, really what happened, people couldn't understand it at all. What they were discovering all these new particles, and what they were finding was that if you bash protons and neutrons together, all sorts of complicated new states start coming out of that, and it's something very, very complicated, and it's clearly that the problem is that the forces between protons or between neutrons have this so-called strong force. So there's this and the mathematical methods we had for describing quantum theories of these very strong forces were not very good at all, and still aren't very good. And so there was a lot of effort to come up with new ideas to describe what's happening, like in these strong interactions between protons and that we were seeing at accelerators. And what people realized is some phenomena that you were seeing could be described if you didn't think about particles, but if you took as fundamental objects not particles, but objects that were kind of one-dimensional, kind of what you call like a string leg. So think of the fundamental objects as not kind of living in zero-dimensional points, but living on one-dimensional strings in space. And that if you tried to write down a fundamental theory in which your fundamental objects were strings, not points, well, these strings could vibrate, and you could write down a classical theory of how the strings vibrate. But then if you tried to turn that into a quantum theory, each classical vibrational mode would become kind of a quantum harmonic oscillator, and you would have a quantized theory of strings. That actually started to look like some of the things people were seeing in these accelerator experiments. So for a while, in the late 60s, people were quite interested in the idea of describing strong interactions using string theory, using this theory of quantized strings. And that, but then in 1973, people figured out how to come up with a more conventional theory of quantized fields called quantum chromodynamics, which actually explained how the strong interactions work very nicely. And by the time I got to college and graduate school, that was the people that were starting to lose interest in string theory, and that was kind of falling by the wayside. And everybody was starting to be trained in that. Well, the fundamental thing is this quantum field theory, and these strings don't actually seem to be any fundamental objects. That doesn't really seem to work. It's got all sorts of technical problems. You really don't want to do that. But then, by the time I left graduate school, which was 1984, people were starting to get frustrated that they had this really, really successful quantum field theory of the strong interactions and other interactions, but they couldn't. The problem of gravity was fascinating people, and people were not able to make any progress on that, and they weren't resolving that. So some people had been working on throughout the early 80s, on this idea of, well, let's give up on using strings to describe the strong interactions, but let's use them to describe, to develop a theory of not where the fundamental objects are not particles but strings, and where somehow gravity will fit into this, and we'll quantize gravity also. So there are a small number of people working on that in the 80s and making a little bit of progress. And then in 1984, about the time I left graduate school, the great genius of our field, Edward Witten, really got really fascinated by this, and he and some others then started working on this, and all of a sudden that became really the hot topic, was the idea that we're going to use strings to describe a unified, not just general relativity, but a unified theory of particles, and of the particles we understand, and of the gravitational field. So it's going to be a quantum theory, but it's going to be a quantum theory not of fields and particles, but a quantum field theory of strings. And that was the idea in 1984. And there was a lot of, very quickly, a lot of people worked on it. I mean, Witten is just an amazing figure, an amazing genius, and he came up with some really striking and amazing, but still quite complicated proposals for how everything is going to fit together. And so that's, anyway, that's, in some sense, that's when string theory really took off. And I would say, I went off and started to work on a postdoc, and my feeling at the time was that, well, this looks kind of complicated to me, and I'm not really convinced by it, but and there are all these really, really smart people working on it, and working very hard at it, and working day and night at it. So this actually seemed to me a very good argument about why I should do something else, and why I should not think about string theory, because last thing in the world I want to do is compete with Ed Witten on some things. So my attitude was, okay, I'm going to ignore these people for a while, and see either they're going to turn out to be right, and they're going to get some serious evidence for what they would like to be true, or they're going to give up and stop doing it and go on to something else. And to make a very long story short, I mean, kind of remarkably, 20 or 30 years 20 years later, they really had gotten, to be blunt, they really had gotten nowhere with this. This was not really working out very well, but they were still doing it. It was still getting, it really, and there's a long story about, I think, why that's true. In some sense, it's true because no one else had come up with a better idea. And so people, and it's a very complicated business, and a lot of complicated calculations you can do and stuff you can do, but and they were finding out some things, but they just weren't finding anything that looked like a solution to their original problem. And so this is when I finally started saying, well, somebody should actually, there are all these popular books about why string theory is so great and how wonderful it is, and how it solves it's going to solve these problems. Somebody should actually point out to the public that this actually really isn't working very well. And so that I got involved in that, and ended up writing this book called Not Even Wrong. And now, I started writing a book almost 20 years ago, and that it came out at the same time as another book by a guy called Lee Smolin called The Trouble with Physics, which was making similar points. So the period of around when these two books come out is often referred to by people in the business as the period of the string wars, when there was a very vociferous public discussion of the problems of string theory and whatever. And so that kind of goes on to this day. I would claim that, I mean, string theory it still doesn't work, and it's not. I think a lot of the arguments that I and other, at least Smolin and others were making about the problems with string theory have held up pretty well. But anyways, I don't know, that's the outline of the story, if you, at least from my point of view.
So 2006, I think 2008, I started my undergrad school. So I definitely came along your book, Not Even Wrong,
Okay.
and Smolin's book. But also Sabine had another book like called Lost in the Math, talking about the idea of like, we are getting too much, lost in the beauty of math and getting ourselves far from, maybe nature a bit. But the thing is, my question would be, in string theory, do they have, what kind of predictions do they have so we can look for them in the universe?
I mean, the physical objections to string theory, I mean, there really are none. I'm sorry, anybody who tells you that string theory predicts something is misleading you. I mean, the proposal that Witten and others came up with in 1984 was fairly specific. And if you look at that proposal, there are, in some sense predictions, but they're really only predictions in the sense that, if you were able to do things to probe, exponentially higher energies than we are able to probe, so now we're able to go up to, what is it, to look at things that are happening like 1,000 GeV, and they said, well, if you could actually go and look at things that are happening at 10 to the 18th GeV instead of 10 to the 3 GeV, then you would start to see these strings vibrating, and you would see this, but they couldn't tell you exactly how the strings would vibrate or exactly what energy would start seeing, but they say, somewhere up there you should start to see some of this. That's really that's it for predictions of string theory. And even that, as people have studied string theory, I mean, the one thing that's kept people fascinated by it is they never really had a fully consistent string theory either. So the whole effort to develop a fully consistent framework for doing string theory has led to all sorts of complexities and new ideas and new proposals, and a lot of these new ideas, those are inconsistent with the picture I just told you about the strings vibrating at 10 to the 18th GeV. So if you believe in brains and various other things that have come out of string theory, you've lost even that small prediction that we would have had here. But the one thing I think in terms of physical predictions, this really has not been a success. I think actually, if there's one there's one book actually by a string theorist which is quite interesting, by a guy called Joe Conlon, about forget what the title is, maybe What is String Theory or Why String Theory or something like that. And he published this a couple of years ago, and he's worked very hard on this question of how do you get predictions out of string theory, and so he has one chapter in this book which is called the experimental evidence for string theory. And I remember when I saw the table of contents of the book, I said, well, gee, that's interesting. What is he going to do with that, and how is he going to talk about experimental? And then, but if you pick up that book and look at it, the chapter experimental evidence for string theory has only one sentence in it. And it says, there is no experimental evidence for string theory.
I have to go and check that book. That sounds interesting.
And this is a book written by a string theorist. So that's all I'm going to say about that. So that's fairly clear. But yeah, so Sabine Hassenfelder, that's a more interesting story. So she, I think I kind of agree. She has making many of the same points about string theory. There's a whole lot of interesting questions about the relation between math and physics and string theory, which yeah, that's a different topic, and where I don't even really so much agree with her. I actually I'm actually much more of a fan of the idea that we can do some, just by thinking about math we can get somewhere, which she doesn't really believe.
Yeah, so kind of like if you go back to the older theories like general theory of relativity, or in the mathematics just started with mathematics. Some of the things were based on Riemannian mathematics, Minkowski, they were just like Or like Dirac, right? Hilbert created the mathematics and said, nobody till I'm alive is going to use this mathematics. And Dirac comes back and says, hey, I just used it in quantum mechanics. So I fully agree with you in that sense, that mathematics, but being completely off of, predictables or testables ideas is a dangerous route, right? So
Yeah. Yeah, I mean, but that's kind of the fundamental problem where much of this fundamental physics research is these days, is that people, on this problem of quantizing general relativity, we have no experimental evidence. I mean, just trying to think, doing kind of dimensional analysis of, how, if there is a quantum theory of gravity, a theory of gravitons, how, what would you need to do to see a graviton? And if you start thinking about that just on dimensional analysis grounds, like, there's just no way you're ever going to see a graviton. There's just nothing you can even imagine doing experimentally, which is where you're going to be able to probe how a graviton works. And so, people have worked very hard, and Sabina, has also worked hard, and she would claim that, well, maybe there's some hope of trying to get some kind of experimental evidence for what's going on in quantum gravity. But that's a really intractable issue of how to experimentally probe quantum gravity, and we don't really know how to do it. And then our problem with, the non-gravitational degrees of freedom, we have, our theory is just too good. We have this so-called standard model, and every experiment we do agrees perfectly with this, and it's just incredibly frustrating. How do you come up with a better model if you have kind of no experimental anomalies to tell you where to look? And so it's a very frustrating situation. So, I agree that, just trying to kind of say, well, I'm going to try to come up with a better theory by just investigating, the mathematical structure of the theory and by kind of pure thought, is not traditionally a promising way of going about things. It's very difficult, but we may be in a position where you actually don't have any choice, and you can't, if it's not, yeah, anyway, it's not an ideal way of proceeding, and it's got its problems, but everybody is frustrated because they don't have anything better, and the alternative is just say, okay, well, let's just give up and wait till 200 years from now when we have different technology and we can actually, maybe something will happen. But
so the thing is, like, I remember when Higgs bosons were being discovered, every single person was holding his breath.
yeah,
Theoretical physicists, one of the professors I know of, they're like, I wish it's not discovered, and so we can have a clue. Something is off with this standard model. So
yeah.
were you the same, like when that one was, the Higgs bosons were being discovered and they actually detected it, right? So
Yeah, I think, when the LHC was being turned on and they're trying to figure out, is this going to see the Higgs? And my feeling was, well, you're really, so we have this theory, and so far everything is predicted has turned out right, but the Higgs sector is something new. It's really different. It's a different kind of field. It's gonna, and the theory predicts very clearly what it's going to do, and there's you basically had a very strong prediction. Here's exactly what a Higgs is going to look like. There's only one thing, there's one number that has to go in the theory, which is the mass of the Higgs. We don't know that number, but once the experimentalists figure out that number, the theory is going to tell us exactly what the Higgs is going to do, what you're going to see. You're going to see a peak at exactly this shape and this width, and it's going to decay into other particles exactly this way. And so I think my hope, and the hope of most people, was that, yeah, there's something, we're going to get around this frustration with this theory by, we know that something's got to happen like the Higgs, so we got to see something, but hopefully that something is going to tell us that, okay, you guys were wrong, and this theory that you thought was so great doesn't actually work quite right. You're going to see some, it's not going to look quite like you expect. And that's what I think most people are kind of hoping, but in some sense, the great thing was, the theory worked out exactly as predicted. So there's this kind of glorious that we had, we predicted something completely new, and what we found was exactly that. That's so that it's a great triumph of the theory, but it's also a great frustration that we didn't get any new hints as to how to come up with a better theory from this. And, but it was a dramatic moment, and I really, anyway, it was kind of fun for me because I actually know a lot of experimentalists. I also actually worked at an experiment when I was an undergraduate, so I have a little bit of background in that kind of experimental physics, and so I could actually appreciate what they're doing. And I was so fascinated by this. I kind of devoted my time trying to figure out what's going on in these experiments and what are they doing. And I actually ended up with having, anyway, if I do say so myself, I think I was perhaps the best source of inside information as to what the state of was going on in these experiments doing at that time in the lead up to the Higgs discovery. And I was very, so I actually was able to discuss on the blog the early news of the Higgs discovery before other people, which was
you got the
it was a lot of fun.
You got the insider news basically early on.
Yeah.
So the thing is, like, so basically what we are talking about right now, the current status of theoretical physics is a bit dramatic. Let's put it this way. We are either kind of, do you think, is there any other way that we can start looking, right? Because the way we are talking, it looks a bit depressing that everything works on standard model and string theory doesn't have any predictables. There are other alternatives like loop quantum gravity. We don't want to get into that one. That's also another big deal, right? Rovelli's team. Right?
So yeah, it's a different idea for how to quantize the gravitational field. Yeah.
But none have been having experimental predictions to be tested. So what do you think? Where should we go from here, right? So,
well, I mean, I don't know. I think, from this point of view, the experimental point of view, I think this really has to be just driven by. I mean, you don't have there isn't a. I mean, the theorist cannot tell you that. Look, you just need the solution to our problems, or figuring out what's going to go on, how to quantize gravity, or to make a better theory is going to come from you going out and doing experiment X, which is possible within current technology. That's just not, we really don't know how to do that, but we don't have a good proposal for that. I mean, what we, to me, I think this needs to be driven kind of by the experimentalists. I mean, people have to kind of figure out, what, as an experimentalist, what technology can you see, or what experimental techniques do you see which are going to let you look into some regime which has not been looked at yet, which has not been studied before, where you can actually potentially see something new. And it would be nice. Unfortunately, the theorists really can't point you and say, go and look at. If you go and look in this direction, you'll find something. And all you can do is say, well, if try to identify things that you can do that you can study, which haven't been studied yet, where and maybe something new will turn up. And so maybe the most straightforward is the what's going on at the LHC now. So the LHC now, it's been shut down for a year or two to try to to make some improvements in the machine, it can go to a little bit higher energies, to higher luminosities. And so they're going to be running it for the next 10 years. And one thing that they're going to be doing is just measuring very, very precisely the Higgs properties. So we found the Higgs, we've measured some aspects of its behavior, but it's possible to do better. You can you can look for more different kinds of decays of the Higgs. You can look and you can measure their the properties of these decays, and there's many things that which we haven't yet seen, which the theory predicts you will see, which you can try and measure and try and compare to experiment and compare to the theory. I think it's kind of a frustrating situation for the for the experimentalists, because they're going to be doing very, very hard work, and the most likely situation is that the theory is going to win, and you're going to just see what the theory predicts. But maybe not. There's no guarantee of that. You know, maybe you will finally find something new. And so that's one example. But I think there are a lot of examples of that. Of, you know, people are out looking for, you know. Anyway, for there are all sorts of different things. There's an experiment that's about to announce results looking for for trying to measure the anomalous magnetic moment of the muon. I think that's the one, the muon, electron, muon, I guess. And that's, you know, the theory has a very precise prediction about exactly what that is. They're doing a very precise measurement, and you know, it would be in some sense nice if it comes out different, but we'll find out.
So when I think about, from my point of view, about the theoretical physics right now, it reminds me of the old time when the chaos theory was coming out, right? So the thing was, so many experimentalists were missing some things as noise, or maybe they were not looking at it even because they were convinced that this theory is working very well and everything is fine. And I think, I don't know why we are in that era again. If experimental physicists start actually going wild and try to find anomalies, right? I think right now the problem is the theories are working too well, and everybody tries to go to, you know, I understand the need of going toward them and more, even making them more valid, let's say, but don't you think we should go a bit wild? The problem is funding for sure, but don't you think if they start going to the edges, we're going to start thinking...
This is kind of, yeah, I mean, I guess the other part of what I should have emphasized with it, yeah, I mean, I think people do need to just, yeah, to try to, if there's something you can measure which hasn't measured before, which is quite, yeah, where you're not expected to see something, but you know, no one's ever looked. Yeah, people should be looking. You don't know. I think, you know, besides like the Higgs measurement, where you've got a well-defined phenomenon, you're looking at. I mean, the problem now is that there are some small number of possible anomalies or possible things which, you know, the theory may not be properly doesn't properly capture, but you know, the problem is that there's a very small number of those, and those are actually getting a lot of attention. So the most well-known one is kind of dark matter, and this is more, I mean, it's more kind of your business and among astrophysicists that you've got this astrophysical evidence that there's some kind of stuff out there gravitating, which we don't understand what it is, and so, you know, a huge amount of effort has gone theoretically into trying to come up with ways of changing our fundamental theory to have some new component which would explain this dark matter, and then also experimentally anything that anybody can think of an experiment that they can do where you would actually test such proposals, that you would see, you know, axions or WIMPs or, you know, or anything, and that's, you know, I think quite rightly people kind of have identified that as the most likely direction where something new might turn out. But I mean, that's also a frustrating field, partly because, you know, so much effort theoretically and experimentally has already gone into it, without much success. So it's yeah. Anyway, I think that's also, but that makes it difficult. But you know, people have to keep pushing.
So that I know that the difference between astronomy for our listeners and particle physics is we astronomers look into the skies and try to capture, you know, anomalies into the universe, that like something like time domain astronomy, which has been started in, you know, going toward the objects that don't make sense at all with what we've seen before. But on the ground, on particle physics, we need to have definitely colliders to study it. And China is coming with a bigger one, right? So they are planning to release, I don't know when is the start date exactly for the project, but do you have what that is going to bring? That's one question I've always had from.
Yeah. Well, the situation is very unclear, and I mean, the fundamental problem is that, you know, the LHC is already a pretty big, you know, a pretty big and quite expensive machine. So it's it's a circular ring which is 27 kilometers and I think in diameter, no, in circumference, And the and the problem is to go to higher energies, there's really only two things you can do. There's only, the technology is such that there's only two things you can do. One is you can, if you want to circulate higher energy protons in that 27-kilometer tunnel, all you can do is you need stronger magnetic fields. So there's basically these magnets which are deflecting the particles and making them move around in this tunnel. And you know, the magnets that were designed and built now 20 years ago were they were kind of the highest strength magnets anybody knew how to build at that you know, at the time, at quite an expensive cost. And the technology is such now that, you know, 20 years later, you know, we arguably, possibly, maybe if we're lucky, we know how to make magnets that are twice as strong. Okay, so one proposal, once the LHC no longer work, is, so what's going to happen about 10 years from now is it's going to stop making any sense to keep running the LHC, because you're going to be accumulating more data, but it's cost money, and the marginal data you're going to accumulate each year is just not going to be worth it. So 10 to 20 years from now, maybe 20 years from now, the LHC will get shut down just because it doesn't make sense to keep running that machine. So if you want to go to higher energies and explore something new, you need higher energy beams. If you want to work in that tunnel, you need higher field magnets, but the only magnets that you know how to design, that you know how to design within the now or arguably the next 5 or 10 years, are maybe twice the field strength. And with twice the field strength, you can double the energy. So the question for the funders and for all the physicists is, do we want to spend a lot of money, maybe, and to fill this ring with new state-of-the-art, you know, very, very cutting edge, high field magnets would cost $10 billion maybe. So the fundamental question, one fundamental question for the field is, do we want to spend $10 billion to just go up by a factor of 2 in energy, and with no guarantee that there's any kind of new phenomenon that we can see in that new energy range, that's really, and it's a very difficult question. I mean, you know, it's a lot of money. It's not clear whether so Sabine Hassenfelder makes the argument that, well, you know, since you don't have a theory saying you're going to see something new, it's just not worth doing. You shouldn't even bother. Other people are like, well, maybe, you know, why should we just give up and not do it, you know, and not even look for anything new because it costs money? And anyway, it's a long argument. But I mean, that's a little bit oversimplifying the situation. There are other proposals are to basically to dig a bigger tunnel. And so if you dig a bigger tunnel, you can go to higher energies, again, kind of proportional to the size of the tunnel. So there's the other proposal that people are talking about is to go out and to dig a 100-kilometer tunnel and fill the 100-kilometer tunnel with these twice the strength magnets. So then you get roughly, you know, a factor of 4 from the size of the tunnel, and you get a factor of 2 from the magnets. So you're going up a factor of 8 in energy, and that may get more interesting, and that people are much more willing to believe they might see something new if they go up by a factor of 8 in energy than by a factor of 2. But again, now you need not just $10 billion for new magnets, but you need another $5 billion to build the tunnel. So it starts to get very interesting. And the Europeans, I think at this point, have kind of gone through a process of saying, well, you know, if you want to go to high energies, this is how to do it. And they're studying, you know, how exactly would you do this, and what exactly would the price would be, and is there any way we can raise $15–20 billion? And the Chinese are actually going through a similar process, but it's not at all clear that the Chinese are going to decide that they want to spend. They have the same problem. If they have 10 or 20 billion dollars, do they really want to spend it on this, or they want to spend it on something else? And it's not so clear.
So the other question I had is there any way that we can start using observations, not creating it on the Earth, but at least looking at something in the universe that will tell us something, right, about the way we should head? Because the gravitational waves are coming in, they are going to give some informations as they come about some space-time interactions, right? So the question is there a way that we can at least start looking and justify, say, hey, we've seen something, now we can go and start build more colliders, right? Or
yeah, the problem is that the great thing about the LHC was that we knew enough about the Higgs. We knew that something was going on. So there was actually almost there was pretty much a complete guarantee. So the energy range the LHC was going to explore, you had to see something new. Either it had to be the Higgs or you had to see something else. The theory was, there was no consistent theory in which you didn't see anything, and anything new. So, but that's not true now. And anyway, well, so it would be great if you but the thing that makes it, the problem is that what makes it this scenario a little bit implausible is that the energy range which you're studying when you get to the Higgs. So what you would like is an argument saying something interesting has to happen, and you won't see it if you look at 1,000 GeV, but you will see it if you look at 10,000 GeV energy scale. And it's just kind of very hard to come up with an astronomical phenomenon that you can actually get some information about, which is telling you to study that high energy scale. And the only thing that I really know about that study about that is you get if you just look at cosmic rays coming to the Earth, the Earth is bombarded by cosmic rays all the time. At a range of energies, almost all of them are relatively low energy on these scales. But they're very, very, very rarely you have a cosmic ray coming into the Earth and hitting something, and an interaction happening where you start to which in principle is happening at at 1,000 GeV or 10,000 GeV. So the problem with this is that those events are extremely rare, and if you look at what happens in a collider, that when you're colliding these high energy particles together, and you're producing just these billions and trillions and trillions and trillions of events, and then the ones in which some energy exchange is happening at very, very high energies, in which are actually something interesting is going on, are extremely rare. It's like 1 in a trillion or something. So your problem is that, yes, you have this astronomical source of high energy particles which is coming in, which in principle you could have access to, but it's just the event rate is like down by a trillion or so from what you need to actually hope to see something the kind of thing you want to see. And also you don't actually know, it's not like a controllable beam. You don't actually know what's coming in, so it's a little bit harder to work with.
So is the one thing I was going to ask again is, can we, so we know in particle we go down to the particles, and but is there a way to study the consequence of the way we are looking at particles in something more high energy, right? Let's say when you have a supernova or an accretion that's happening, is there a way to look, what is the consequence if I look at it this way, and reverse engineer and see if anything is coming back to me and helping me to understand, justify my decision to go put $15 billion to make a collider?
I have to say, a lot of the problem here is that, despite my spending time reading books about technical astrophysics and modeling stars when I stopped doing that when I was about 17, 18 years old. So I don't, so my knowledge of what, high energy astrophysics can do is minimal. I mean, one thing which I think, one interesting thing that might happen any day now, or could happen any day now, is that if we have a nearby supernova, so we have these huge tanks people are looking at that are trying to look for proton decay and stuff. And if it was at 1987, the last nearby supernova, they those early versions of those experiments actually saw, when there was a nearby supernova, you have a huge neutrino flux coming at you. And people actually saw neutrinos from the supernova, and the structure of when they came in and their energies and what you learn about those was very, told you that some very interesting things about neutrinos, not just about them. So it's not entirely impossible we'll actually learn something new about neutrinos. Actually, maybe I should talk about, that's another interesting stuff. We don't completely understand neutrinos, so there's a lot to learn about them. And I would, I think there's, anyway, you may have a supernova in a nearby galaxy or a galaxy sometime tomorrow, and we might actually learn something about super neutrinos because of it, very directly.
Interesting. So now I think, so you think we still have hope for theoretical physics going forward. And I believe in that myself as a physicist, that there is always hope. There's going to be some way, an anomaly one day jumping in that is going to baffle everyone. But it just needs to happen if everybody widens their eyes and start looking.
Well, that's true. I mean, I think, I think, but as a theorist, unfortunately, I don't have any very good advice to experimentalists. I think they really have to, and I certainly hope that sometime you'll see it. I mean, a lot of what I've done, one reason for writing this book, Not Even Wrong, was more internal to theorists. I think, a lot of the problem within theory has been, that people have spent, now 30, 40 years really, really focused on a certain kind of speculative idea about how, how we're going to get a unified theory and deal with gravity. And, as long as people, if that idea is not working and no one is willing to kind of admit that it's not working, and people are still keep pounding on the same failed idea, that's really not, you're not going to see progress just because people are clearly doing the wrong thing. So a lot of what I was doing for many years was trying to make the point to people, look, you really have to look clearly at these claims about this theory and about what, and understand what, what it works and what doesn't work, and be honest about that, and really, and use that to change the focus purely within theory and within more mathematical theory to get away from things which don't work, and to focus on things which may work. And I should say, actually, personally, within the last year or two, though, these ideas about twistors that I've been working on have just worked out far, far better than I expected. And I'm very, very excited about those. And I find myself in a very, very weird position. I've spent most of my career, like, literally almost every day I get an email from somebody saying, oh, I have this great new different idea, and it's going to unify physics, and it's so wonderful. And they're all, they're from complete cranks to ideas which really don't work very well. And I mean, it's the whole, but I've just seen infinite amounts of this, and now I'm like, wait a minute, oh, I see all this really interesting idea here, and I'm very excited about it. I want to tell people about it, but I know very well what this sounds like to everybody, because I've seen, anyway, I've seen a lot of this, and it's all not really promising, often very cranky stuff. So I'm trying to figure out how to deal with, how do I get more, how do I get this stuff written down, and how do I communicate to others and to people in a more convincing way, that and not, how do I not sound like the kind of crank, which I think I probably do sound like. So, so that's the very weird position I find myself in right now.
Yeah, I very well understand like what you're thinking, because when I still get those emails as well, that
Yeah.
somebody emails, puts gravity equal, I don't know, electric field, and says, hey, look, I combined electric field with gravity. I'm like, yeah, so you know what I mean, right? But the thing is, like, the way you're looking at it, I'm actually very interested, because the thing is, twisters fall in 4 dimensions. They don't add any extra dimensions to our universe. Quantum mechanics is there, and if you actually come up with a way to combine them, I am pretty interested to read that paper. That's gonna be it.
This is yeah, there is it's great. The problem is that a lot of the mathematical framework is really not something that people are used to, and as I said, so in these yeah, it's really not what people are trained in or what they're used to. It's not yeah, so I think the reaction, I mean, I wrote a preliminary paper, which I kind of think is version 1.0 of what I'm doing. Now I'm trying to finish version 2.0 of it. And the reaction I got some useful reaction from some people, which was mostly kind of, incomprehension, like, how could this possibly, you're not really explaining in enough detail how this could possibly work, but there's something, there's a part of the story which is kind of unexpected, which is not, I think, the way people would have expected this kind of thing to work out. It's purely a theoretical mathematical question that I hadn't. I could see that this was not working out the way that you would expect, but I hadn't completely figured out exactly how it does work out, and that is something I've figured out a lot more about. I'm trying to write out, but the reaction I got from a lot of some very good theorists, I know, was that, well, yeah, maybe, but we can't understand exactly what you're talking about. It's just too and you're claiming that something unusual happens here, which we wouldn't have expected, and you need to provide more evidence of that. So that's the level at which reaction I got, which was fair, but I think it's mostly been kind of in comprehension, but there's trying to figure out it's clear I need to kind of work harder at kind of myself understanding things better and explaining them better. But then the other interesting question to me is, how much do I then want to kind of promote this? Say, look, if this is right, this is really mind blowing. This is really going to change this, but do that while not sounding like a complete crank. I don't know.
I mean, you have a lot of credit. So the thing is, when I was undergrad, I was working on brand stick theory. I'm sure you're aware of the higher dimensional, like brand stick theory and other theories, that brand sticky theory, that other theories, with the higher dimensions. And during my undergrad, I was a very naive physicist, so I was very interested in this objects, and then these theories. I ended up coming to a quote from Hans Bethe, saying, give me 4 polynomial with 4 degrees, I'll fit an elephant. So there I started thinking, wait a second, am I just keep adding more parameters to fit the data here? So the thing is, like, the one thing I like about your approach is because it's keeping the dimensions 4. It just not keeps adding dimensions when it's stuck. That there was a professor I visited one time in another university. I was grad student. He was saying, string theory, whenever they get stuck, they add a dimension. And standard model, whenever they get stuck, they add a particle. So I just remember that joke.
Yeah, that's true.
But then your approach looks very promising. I'm really looking forward to it, Peter.
I mean, I think, I think the simple way to understand kind of why string theory proposal really doesn't work is that it's one of these higher dimensional things. The idea was always that, well, strings make the most mathematical sense in 10 space-time dimensions, let's say, and so then all of the physics that fit the standard model and the particles we know about are going to have to do with what's happened, with how you deal with these extra 6 dimensions. And at the beginning, there were some very specific proposals that there's some tightly constrained way that will deal with the 6 dimensions, and that'll predict something. what really ended up happening was really just people just found more and more things you could do with the 6 dimensions, and you end up that there's so much you can do with the 6 dimensions that the theory ends up being, it really can't. That's why the theory can't predict anything, because how you handle the extra 6 dimensions, you can get anything you want. So that's the fundamental problem. And yeah, this is one of the appeals of the Twister program, and whatever, that this is really that it's a geometrical setup which works purely in 4 space-time dimensions, and that it really doesn't in any nice way. It doesn't work in other. Doesn't work it. Yeah, it doesn't work. It doesn't work in more dimensions. Which is one reason actually the string theorists traditionally never really liked it, because it's like, how can we, once if we try and take those techniques and use them in higher dimensions, they don't really work so well. So.
So I remember, to the level this extra dimensions goes, I've seen papers. That's why I'm saying the theory, some parts of the world, the theory is going too independent of the world. Like I've seen physicists who create Lagrangians based on a manifold, a new topology, and try to find the black hole solution for it. And I'm like, so what am I gonna look for using this, right? So I understand it's speculations going around, but it becomes a publishing business rather than like doing physics, right? So
yeah. Yeah, well, I mean, this gets back to, the problem is that I'm actually more sympathetic, and especially coming from the point of view of mathematics, I'm actually more sympathetic to the idea that when you're stuck and don't really know what to do, then you don't want to be too constrained by saying, I'm only going to look at things that that work, that I know are going to work the right way. You want to actually try to see if you can follow your nose and find some new ideas and calculate some things. Let's see what happens if I throw in extra dimensions. Let me just work with these exotic kinds of black holes, which I know can't be physical, but at least I know how to calculate with these guys. So there is an argument for that kind of process, but it certainly can go too far. I mean, it can become just its own self-generating industry if people are just keep calculating stuff because they can calculate it, even though it clearly is not working, and that's the problem.
So my point is, like, in that sense, because there are young minds, fresh minds who come to the field, and they get stuck in the publishing business because they just have to follow the footsteps of continuing this math without even thinking. I remember I was referring one paper, like I just, because of my undergrad work, I got involved. They were getting lots of physics out of one parameter. And I was just questioning the physics behind this parameter. What is the units behind it? And I got a fascinating response. They didn't know what unit it has. So I was like, wait a second, you're getting physics out of this. It just, that's the point I'm getting at. In some parts, it's too far from physics that it started going in a way that they don't think about, wait a second, what am I gonna predict using this, at least?
Yeah.
It's nice that it's nice to be speculative, keep going, but there should be a point that you need to say, wait, I need to double check the reality a bit.
But it's also I guess my feeling, a lot of the problem of speculation also is more that arguably what we need is people. We need maybe more speculation, but you need. And this is one way in which I actually think that mathematics is much healthier than physics, is that mathematicians traditionally, the culture is very, very much that you try and become expert at something, but you try and become expert at something different than everybody else. So what happens in physics traditionally is there's some new idea or some new experimental result, and it looks kind of interesting, and so everybody then kind of jumps on that, and everybody tries to work on that. Mathematicians behave very differently. That there's some new idea will come up in mathematics. If it's related to what you've been working on, people will start thinking about it. But you don't have everybody jumping on the same in the same subfield, in the same, on the same idea. And there's a lot more respect for the idea that, you know, it's really, really hard to come up with something good and new. And if you just kind of jump in on something, you know, unless you're Ed Witten, you're not going to accomplish something really valuable by just changing what you're doing and jumping on some new idea you've heard about and jumping into that, and 3 months later writing a paper about it. It's not, the chance of that actually working out are not good. So that you should actually focus on trying to find a new idea and find something new to do, but that's not the same thing that everyone else is working on. If you're, so you should try to stay away from fads and stick to trying to get deeper into what you know about. And so it's a different kind of culture. And mathematicians, you know, they publish fewer papers. They don't have the same. Anyway, it's in many ways, I think, a healthier culture, and it's different because mathematicians have never had experiments to tell them what the right thing to look at was. They kind of had to, on their own, you know, come up with their own
thought experiments,
their own ideas and their own, you know, their own understanding of what is known and what isn't known, and what exactly where the boundary is, and how are we going to push the boundary in some direction to come up with something new. And physicists just haven't, they've had kind of this luxury of, you know, you turn on a new accelerator and these new particles that nobody expected came out, and everybody can jump on and trying to understand that. And so you can afford to have this very faddish kind of culture, which mathematicians have never had the luxury of having.
I mean, in the older times, you know, the physics and mathematics were not too separated as they are right now, right? If a good physicist was a good mathematician, and a good mathematician kind of was a good physicist as well, like back then. But now it's just became so, as you say, and that's what I've seen. The funding goes toward the mainstream ideas. They would not try to fund a grad student who suddenly comes in and says, I want to question everything. I'm going to sit down and do something extraordinary, right? So
but it's true, and especially I think when you've got really difficult fields in a really difficult position, the kind of standard model of a career where you expect, you know, anyway, I mean, there's standard expectations that, you know, if you're a graduate student, you're going to publish these many papers. You're a postdoc, you're going to publish these many papers. You're going to do this. I mean, you know, to fit into kind of the standard expectation of how you're going to, of what you expect to see in a successful academic career, that's all kind of built upon, you know, assuming that the field is healthy and that and that, you know, it's making continual slow progress and it's moving in a good direction, and everybody is just, you know, people are doing their work at slowly at moving in this direction which everybody agrees on. If everything is kind of moved in some direction which isn't working, then, you know, what are you going to do? Do you just kind of keep people looking at people and rewarding them for, you know, their extra small efforts in the wrong direction, or do you how do you encourage them to try to work in a different direction? And how do people have successful careers like that? It's very hard.
So the way I see, since I moved out of academia, I'm working in industry now in artificial intelligence. The way I see the academic right now, in that sense of theory, the way I see it's like a reinforcement learning robot. That, you know, you're trying to reduce the exploration, but increase the exploitation. You just keep overtraining over one thing, right? If you a bit like knob it up toward exploration to your grad students, this should make a big difference in a couple of generations.
Especially you want the people who are just starting out, you know, to some extent you want them to start out fresh and not get stuck in the same thing. I should point out, I mean, I actually have a slightly weird career besides the career of moving. And so I was a postdoc after being a grad student at Stony Brook, I was a postdoc. Now, a grad student at Princeton, I was a postdoc at Stony Brook, and that was when string theory became so fashionable. And, you know, I wanted to work in this boundary of math and physics, and I was talking a lot to mathematicians, and it became clear that, you know, that just what I was trying to do was just, there wasn't really any room for it in physics. Physics, you know, the physics, my chances of getting a decent job in physics were becoming from slim to none if I were trying to do what I wanted to do. And I, so I realized, okay, well, wait a minute, but the mathematicians they're getting more interested in physics. So I actually managed to kind of shift over to mathematics but even, and I got a job as a postdoc in mathematics at Berkeley for a year. And then I came to Columbia as one of our kind of teaching posts, non-tenure track assistant professor here for a while. And but again, it was clear that what I wanted to do still did not, it also didn't fit in the model of what a mathematical career was. And so, after I'd been here for a few years, my job was coming to an end, and but the department needed somebody for a weird position here, which is kind of your responsibility is teach one course and make sure the computer system runs. And I've been doing that now for 25 years, and under a weird. So technically, I'm a senior lecturer, so I'm a faculty member, a senior lecturer, but it's a weird position where I'm not. My main evaluation is, does the computer system run? So as long as the computer system runs, people are happy with what I'm doing. And I don't actually have to worry that people are not sitting around and evaluating me. Is this guy writing papers? Is he doing something that fits in the right? So I've managed to get myself in a position where I can actually do what I want to do and pursue it in the way I want to pursue it, and without kind of, but it's an unusual thing. It's not a freedom that people normally can have in this kind of academia. And I really enjoy working here. The department is great, and I've learned a huge amount just by teaching. I've been able to kind of teach courses in which I can actually learn things I need to learn, and it's been a great experience. But it's not one that kind of fits in the normal pattern of academic the academic careers. So I've been off on this other very unusual track, which
is very interesting, right? So when you look at the older times again, the people who were not in that track were sometimes bringing shakes into the science.
But I think that's one thing about academia has become much more. It's become much bigger and much more organized, and there are huge numbers of PhDs. And I think there was much more of a possibility in the past. If you go back 100 years, it was much more okay. Somebody, there was a small community of people. There's a small number of people getting PhDs. It was a small community of people. There was more kind of freedom of people to follow, to follow a path which was not so conventional. I mean, as long as as long as other people thought, okay, this is a reasonably smart guy. He seems to be doing something interesting. You might find a place for you in academia somewhere. Whereas that's harder these days, which is too bad.
Yeah, it is hard. That's why I myself left.
And mostly, I find most of the people I know started out in the field ended up of leaving, and it's not a. Anyway, I mean, part of what I often worry about when I was writing about it, and it's not even wrong, but I even wrote about this question. What can you do to kind of change the reward structure of this field? And I should say that's something which I've never gotten. Hardly anyone in a position of any responsibility seems to take this as seriously as to really thinking hard about what they can do to change things. But because it's difficult. There isn't an obvious thing to do, and people. And the other problem I found is that people, people who the funny thing I found now is that actually the people who are my friends and fellow students, whatever, some of them, the ones who stayed in the field, they're now actually in positions of fairly great serious authority. They're now people running things in the subject, and I can see from talking to them that they're even to the extent to which they're sympathetic to the idea that we should really change the way we do things. They're operating under very tight constraints. There's a fairly rigid system they work under, and one of the problems with this rigid system is that you really don't want to admit that things have not worked out very well. That the minute other people get the idea that, okay, something you've been working on has not been working in the last 20 years or whatever, all of a sudden, you know, the NSF is going to stop giving you money. Your colleagues are going to stop hiring anybody in your students. You know, it's really, it carries a serious professional price on your ability to do anything, to admit that this research program has not been working out. And people are very unwilling to admit it, not just because people do not like to admit they're wrong, but also because of the really serious cost that the whole system imposes upon anybody admitting that something that they've been doing hasn't been working.
That's exactly what is happening. So I'm originally from Iran, and I know other countries as well, which don't have too much experimental facilities, right? And the completely the way of doing science changed from quality to quantity in some of these institutions I'm aware of. Like they just say, how many publications did you get by the end of this year?
Yeah.
It becomes very dangerous. It becomes a business rather than research work. Like there is it's not bad at all to let people publish what if they couldn't get any results out of their experiments. They were expecting something, it completely failed. There's no statistical significance. If you publish that, maybe 100 other groups will not repeat your mistake. But there's no journal in the world that will publish such a thing. You know,
that's the experimental version of the problem. Yeah.
There's no, like, imagine if there was a journal, maybe somebody should take this as an idea and make a journal and call it like literally, wrong physics, like, or wrong whatever. Just put it here. Let's see what didn't work, because most of the minds get stuck doing the same thing over sometimes, and they get published in different journals, and you end up saying, oh, they're exactly the same, right? Some of the things, the assumptions.
Yeah, I think it's the same in a lot of fields. Even in mathematics, it's the same that they're, if you try and do something new in some area of mathematics, what you often spend a lot of time you're doing is you have some idea, say, okay, let's see how that works. And you spend time working on that. And then, after 6 months or a year or whatever, you realize, that can't work for this reason. And, you've learned something. But the problem is that something you've learned is not publishable. And so you're not, and the problem is that it also, what you start to realize is you realize that, anybody who comes into this field probably sees this idea and says, look, I can try and do that. I mean, the way the culture of mathematics actually ends up working, what's actually good is that, people, when they come into a field, ideally, they're working with somebody more senior. So there's some senior person who's been around for a while, and he's tried to do all this stuff, and he's realized why these things don't work, or maybe his advisor explained to him why this doesn't work. And so, there's a culture then of when mathematics is really operating, the mathematics research culture is operating the way it should, or the way it in a healthy way, then people coming into the field are trained by people with more experience who actually know, they know the story about which things don't work, have been tried and which things don't work, even though there's nowhere you can read about them. There's no papers, there's no books, there's no nothing, but there's a kind of an oral culture of these people who really are experts and who really understand all these things that don't work and why they don't work. But I agree, even in mathematics, if that culture could be put into print and to help, it would be very helpful to people. But no journal will publish this.
Exactly. Like I was reading one time about this like some scientists are under so much pressure, some grad students, some not they are anonymous. I didn't read the names, but they want to make sure that the experiment has a statistical significance, the p-value, no matter what kind of parameters they tweak. They want to make sure there's a statistical significance, because if they don't publish, they'll perish, right? So if somebody comes up and makes a journal and calls it whatever, if it is wrong, if there's no, put it here, right? So let other people see what did you learn, right? And exactly when you say not even wrong in that book that you published in 2006, it kind of has both sides of the argument, right? We not only are going too much to our theory, but on the other side, we don't let people talk about what is not working, right? So
okay, that's an interesting. I actually hadn't really thought of that interpretation. That's great. That's great.
Yeah, I remember when I was reading Not Even Wrong, I was thinking this is like, oh yeah, and from that time on, I've never seen anyone coming and saying, look, my experiment failed, and I'm happy I published it and people know why it failed and what I learned from it. I never heard such a thing. So I hope listeners, whoever has authority, like they can go and make a journal and let people publish like this.
Yeah, that would be. Yeah, but there's analogous things in physics and in mathematics and in theory also. It's the same thing, that there's a lot of theoretical ideas which aren't, which really don't work, but there, I think theoretical physics has this continuing problem also, that people don't it's the same thing. So what happens, somebody works on some theoretical idea and it doesn't really work the way they hoped or whatever it was, but they're like, oh, but I got to publish something. So they try and pretty it up and make it look like there's something not so bad there, and then publish it. And then, but they've never made clear that, well, things, this kind of thing can never really do what you want for some reasons which they think, because if they'd written up the paper saying, well, I worked on this for a while and I finally realized why this can't work, and here's why it can't work, people don't want to publish that. They don't want to hear that, oh, yeah, you had a bad idea and it didn't work. I mean, that's not, so both they don't want to publish it, and also nobody wants to fund it. So
the thing is, like, what happens in this sense, we become one of our eyes are fully blinded. My understanding is, because what happens is we want to look for anomalies to start thinking theoretically to explain those anomalies. If somebody is wrong in his mind and comes out and sees something is not working and he can't publish that, maybe that's something that didn't work is actually an anomaly that's going completely so like it's like half of science, a lot of science goes away, right? Because
well, that's, I mean, the little experience I have in doing organic experiments, I realize it's very, I remember seeing one experiment that I worked on. What happens is there are plenty of anomalies, but the problem is that and then you see an anomaly and they say, aha, I've discovered some great new thing, but the anomaly is just because you made a mistake and you're and so I think if you become a serious experimentalist, my impression is that you become trained in that, if there's an anomaly, the last 50 anomalies that I saw all went away when I properly understood what I was doing. So probably if you're a good experimentalist, you got to figure, well, this one's probably going to go away too, and I shouldn't get too excited. But so I guess then there's a tension between actually not trying to, you don't want to publish an anomaly which is just because like these people with this opera experiment where they had a cable which wasn't plugged in properly, and so they were finding neutrinos going faster than the speed of light or something.
I remember that one.
Yeah, so you really don't want to do that, but on the other hand, you don't want to ignore it and say, it's just probably mistake is going to go away. So yeah, it's a hard.
I think we learn a lot from failures than we think. That's the thing. I hope the culture changes and people can publish those things, because then other people will go and see what didn't work, right? So, and they will be aware of some techniques that didn't work, or maybe they were doing something completely different, but now they see a contradiction, right? That may cause another person see a contradiction with this thing, and then opens up a new, completely new avenue. But when we don't have those things published, it's just, they don't exist. If I am doing something, I don't see anybody else trying it and where they failed. I may see those failures so I can have an idea of moving forward with a different understanding.
Yeah, that's true.
So I think, Peter, I don't want to take so much of your time, but so just a question for you is, if any person who's hearing wants to become a theoretical physicist, because we talked a bit, we were a bit negative for a while about theoretical physics, how it's going, but there are lots of positives to it as well. It's just like, we were talking for past 10 minutes about it. So what would your advice be for a person who's starting to think to get a career in theoretical physics?
I think one thing to say, which I tell to some students, is that if your interests are similar to what mine have been, in that you're very interested in more kind of the mathematical side of it. If you're also interested, let me say it this way: if you're also interested in mathematics, you'll find that in mathematics departments these days, there's often quite a lot of interest in physics there. So it actually is possible to have a career as a mathematician in a mathematics department, and where you can spend a fair amount of your time thinking about problems in theoretical physics. It's a different culture, it's a different way of thinking. You have to enjoy that. But on a purely kind of career advice, what's your chances of getting a job thing advice, there are a lot more jobs and the culture is a lot healthier in mathematics. It's just anyway, it's just, if you get a PhD in particle theory these days, if you get a PhD in theoretical mathematics, you're more likely, you're significantly more likely to be able to have a kind of a reasonable kind of career as an academic, if you want, in if that's what you want to do in mathematics. So if you're at all in the middle and at all find mathematics congenial, consider getting a math PhD instead, and then there's an interesting question of how to, of which fields of mathematics there's interesting overlap with physics, or where you can do some things related to physics. That's one piece of advice. Within physics departments, I mean, it's a very difficult situation. You really, the standard career paths, I mean, the way I was trained or whatever, to go to places like Harvard and Princeton, and then you get a PhD in the theoretical physics, then you got to try and get a postdoc, then you try and get a permanent position. It's very, very, very difficult at this point to do that, and to do that in any way. I mean, the only ways of doing that involve kind of getting involved in kind of research programs which aren't really actually working out very well, and trying to prove yourself in those. And that's not, I don't know, I don't think that's actually such a great way to spend one's life. I mean, if you really, you should anyway. And if you want a career in academia, then, I mean, I've explained what I ended up doing. I mean, I do think there is some room in academia for more unusual stories. That if you, if you're a bright person and get your PhD and are doing something interesting, you may, anyway, people may find room for you somehow in academia somewhere, but I think you're going to find the normal career path is quite challenging at this point.
It's very
maybe it will become healthier and maybe things will change, but yeah. So anyway, I don't know if any of that's helpful to anybody.
So traditionally, at the end of the podcast, I usually ask the guests, what is their favorite book? What book, when you read, you put it down, you were like shocked, it just completely baffled you? It's hard, I know, but
yeah, part of it's been such a long, yeah.
You write a lot of book reviews, so I know it's gonna be very hard for you.
Yeah, I mean, there are a lot of Yeah, I write a lot of reviews. I'm trying to think. Yeah, so one question is kind of books that I've seen recently, and then the other question is book. I'm also trying to think back to when I was a student and
Yeah.
when I first got interested in this, and so the things that had most influence on me when I was starting out, I think often were actually some books about quantum mechanics and also about the history of quantum mechanics. I think it's a very, yeah, I don't know, it's almost kind of a very inspiring and romantic story, kind of how people figured out quantum mechanics during the early part of the 20th century. It's a really amazing story. So I'm trying to think of unfortunately, I don't know of any really recent good books about it. Or part of it is just because I now know that at some point I knew that history so well, I could have stopped looking at any books about it. But yeah, that's just what is it?
Was it Heisenberg's book or like
Yeah, there's yeah. So Heisenberg's book, Heisenberg wrote some books about it, and it is a yeah. I would look at some of Heisenberg's books about that. I forget what they're called. Beyond. I don't think I have any.
yeah, beyond something. I remember in undergrad I
Yeah,
read something too.
yeah. So some of Heisenberg, but the Heisenberg thing is a bit weird though, because some of what was very at the time was very inspirational. So he explained. So Heisenberg had I mean, well, he was one of the first ones to come up with this kind of seriously new correct idea about quantum mechanics with his matrix mechanics, but the whole story of kind of how he was philosophically interested in these topics, and he was learning this stuff, and everything was changing, and how he came into this. It's just an amazingly mind-blowing story, amazing. But some of it is a little bit disturbing, actually. Later on, when you start to think about the history. So I mean, some of it was also so this was all happening in in the early 1920s and kind of early Weimar Germany, after the war. And, he's telling these stories about, this, well, there's kind of fighting going on in the streets, and, he and various other people, like him would get together and go for long hikes in the mountains and talk about philosophy. And then, this all sounds really appealing and really great. And then you start to wait a minute, young German men with blonde hair and blue eyes getting together to go on hikes and talk about, the world. And in the 1920s, this a lot of these people, this is kind of what turned into the Hitler Youth. I mean, this is really not. There's a disturbing aspect of all this, which became clear. So anyway, I had this weird reaction to Heisenberg, and Heisenberg as a story. I mean, he wasn't really a Nazi, but he did work with he stayed in Germany and worked to support the Hitler and on the atomic bomb project. And it's a very weird, complicated history. But yeah, I mean, Heisenberg's books about his experiences, growing up and making these great discoveries, and were hugely inspirational. But there's this weird aspect to them too, also.
Yes, exactly. Like I remember they were called the bikers or whatever. Like they would just go and talk about bikers. Or in the book it says we were biking all the way to the hills and sit
Yeah.
and
So they're
talk.
very interested, but it was this kind of, they're very interested in kind of physical activity and physical culture anyway, in a way which in retrospect, if you look at some of the history of the time, is a bit disturbing.
Yeah, so
Physicists and mathematicians have always been people. They often like to go hiking, and that's fine. But anyway, it was a very, very, very weird and very dramatic times. And so I think it's that anyway, that history I think is fascinating, and just to learn what happened between especially the history of the 19 teens and 1920s in physics is just an amazing story, and also the story of general relativity at the same time from Einstein's point of view. So that just to really kind of learn some of that history is really inspiring.
if you know any book that you like in that subject, please let me know. I'll put it in the description so people can check. The other thing for the listeners, Peter has a very nice blog called Not Even Wrong. I follow it weekly and I try to see what comes out of it. I haven't written comments there, but I write like reading. And I've got a lot of book suggestions from your blog. So I have them. Usually when a new book comes, Peter is the first person who almost catches it. So
yeah. One interesting thing about writing my own book and also writing a lot of book reviews is that I also hear a lot, I often hear about things before other people, and that, either the people who are writing a book contact me about it or send me a copy about it, or sometimes the publishers will say, hey, we've got a book you might be interested in. So I often end up getting, trying to think. Yeah, so maybe just to say a fun thing to look forward to. Publishers recently sent me a new book about Hawking, and it's coming out in April, and it's it takes the opposite point of view. Instead of going on about what an incredible genius Hawking was, which in ways it also points out that there's other aspects to Hawking's story, that he's also a huge amount of kind of promotion of the Hawking myth going on. So this book is called, let me recommend for fun a book which you can't buy yet, which you'll only be able to get in April, which is called Hawking.
Hawking. Okay, I'll definitely put it in the description, but I hope nobody comes after me.
and it's called, and the author is called Charles Seif, S-E-I-F-E, and I think he teaches at NYU, but anyway, it's something I just read recently, which but I'm under compulsion and to try to be nice to publishers not to write about their books until they're available. So I can't, on the blog I'll talk about it, but I won't. I mean on this podcast I'll talk about it, but I won't. I won't write about it on the blog until it actually comes out, which is sometime in April.
So I'll have to cross my fingers to where it comes out to get my hands on it.
I'm not arguing that that's the greatest book out there, but it's an interesting one, and it's kind of fun and something if you want something to look forward to.
Sure. And so I think I'm not going to take up much more of your time, Peter. Thank you for joining us.
Hey, thanks for inviting me. It was an interesting conversation.